welcome to this afternoon session. And first speaker is Nati, Linial, and he will tell us about something local combinatorics and what to do with all these big parameters.
Okay, so I normally start my lectures by saying that please feel free to ask and make comments. Are we on?
Yes, we're
on. Okay, good. Okay, so I normally start my lectures by asking the audience to not be shy and ask questions, but I think with this audience we're doing fine. So again, but the principle remains: don't wait till the end. And besides, I'm pretty sure that I won't be able to cover everything that I wanted to speak about. So it's okay. We will go as far as we can. So my main purpose is to highlight two sets of problems. One is fairly easy to explain. The other one is easy to state, but more difficult to understand what is standing behind them. And do two things. One, put these problems in context and show that they really are connected to lots of things that I think many people here care about. And B, illustrate that they're quite mysterious and challenging, and I think should and will occupy a good deal of research in the future. So just that, in case you like, to wander around in your mind and not so much to concentrate, let me ask a question, and then you can go back to this and so on. But I will get back to this. So here's a specific. I want to start just with a small definition. G is a graph, and all my graphs, well, not all of them, but the graphs in which the game is taking place, they're always going to be large. And I will be specific about this as we proceed. So G is a large graph, and K is an integer. And I want to speak about the K profile of G. What is this? Well, there is a list, H1 to HM, all different isomorphism types of K-vertex graphs. And you ask, how often do we find each one of those in here? So this is a vector. So the K profile of G is a vector P1 through Pm, which tells you Pi says if you at random pick K vertices in G, what is the chance that the graph that you hold in your hand is an object? So a very fundamental problem, which is what I would call a basic question in local graph theory, is what does the K profile of a large graph look like? So this is going to be a very basic question around which much of what we will do today will revolve. So that's question one. Question two is a little bit more vague at this stage, and we will get back to that. I think this should be perfectly clear what the question is. Question two, so this is a local to global. Asks what, so I'm explicitly saying this is at the moment not very well defined, but we will get to that. We will make this question concrete. So what global properties of G does its profile encode, or what global conclusion can you draw from given when you're given the K profile?
Sorry, is KM?
Yes.
No. K is, we're looking at K vertex subgraphs, and there are M different graphs, and different isomorphism types of K vertex graphs.
And these are all different.
Yeah, that's a complete list. That's a complete list. Okay. So this question is, I think we are among friends here. Somebody said, we know that theoretical computer scientists like to tell the rest of the world that they do something practical. Well, not always this is 100%. But here I must say this is honest. So I think this is a question that, at least for me, is motivated, if nothing else, by my interest in bioinformatics. So let me speak for a minute or two about this, because I think this is one of the things that makes this kind of question really interesting. And this is a really, so that's the second part of my title, how to read large graphs. So let us go back a little bit and imagine for a moment that the whole field of statistics, still doesn't exist or just starting. And somebody comes and shows you a million numbers that came from something, from observing people, from observing animals, from whatever. And asks you, what can you tell me about the thing that I have observed? So we know, I think you don't need a lot of mathematical background to say, okay, let me draw this distribution. And then I have a list of, perhaps I will start to work out which distributions are interesting for me. And I work out, and I, perhaps in this case, say, after I prepared the little mathematical background, let's just say, well, this looks pretty much like normal. Perhaps I'll evaluate the parameters. Perhaps this, I can work back and look at the objects that were observed, and so on and so forth. So this is really, a very crude description of what the probabilistic or the statistical point of view is telling us. But what happens now in I think many areas of science and engineering and so on is that what the observation gives back to you is not a long list of numbers, but often big graphs. So just to be concrete and give you one example out of many. So I want to say this is an important question, and I certainly do not claim that I know a solution to it. I only want to suggest a direction in which we can go, but the question is honestly and really important. Instead of this, you get big graphs. So as an example, concrete example that I was somewhat involved with, but there are really tons, so I'm just mentioning this because I know this firsthand. So protein-protein interactions that come from biology. So you have some organism. You don't need to know any biology to understand what I'm saying now. Then you all know that proteins do essentially all the biological functions. Human, well, depends how you count, but let's say 25,000 or 100,000. It depends exactly. That doesn't matter so much. Proteins are in this particular organism or another organism, and proteins come in contact. And you describe this whole thing by means of a graph. So now you have, let's say, a graph with 100,000. So what replaces this is that you get a graph with 100,000 vertices. And really, what do you do with it? So I'm honestly saying this. I think this is a major challenge for today's science in more than one field. And I think that to a large extent, we don't know what to do. So people are doing all sorts of things with it, but this is a major problem. And one thing that also it is being practiced, it's not a new suggestion at all, is so what to do with big graphs. And I'm trying to be perfectly honest here. I'm not suggesting that that's a full answer and so on, nothing of the sort, but at least an answer, a decent answer, is that you can look at exactly, you have a big graph, you look at the K profile, and now you have something similar to what we've been doing in statistics. Perhaps you have a list, not too long, of generative models of graphs, which are the analog of a list of the important distributions that we study in statistics and in probability. And then perhaps you can try to do something similar to this. Then you can say, aha, this is such a big graph from this profile. I can guess that this is a graph that was generated by this and that process. I'll work back, what the critical parameters are, and perhaps I can. So you understand the idea.
Are you thinking of dense graphs or sparse graphs? Because
in fact, okay. But the short answer is dense. But let me just say that, of course, all these questions are interesting and relevant for sparse. And one thing that you can easily, so let's say in this situation, one thing that's just a little exercise with inclusion-exclusion is that if you understand the same profile just for connected subgraphs, then essentially you know everything relevant. So in those cases, you would probably want to, to look at just the connected graph. So these are and of course, if we have good answers here, which we haven't perfectly formulated yet, then this is certainly very useful. So this is one reason to believe that this general question is indeed significant. So just to connect back to things that we've already seen today, of course, this is at least conceptually closely related to property testing, which I don't think I need to define for this audience. But let me just say, let's say take one of the classical things, bipartiteness. So if you think about it, the fact that we know that being bipartite is something that can be tested, this means that the K-profiles of bipartite graphs, so this distribution, or such distributions, are, well, almost disjoint from those that are epsilon far from being bipartite. And in fact, I think there is, even in this area, there are interesting questions to ask. So to what extent, I mean, how large does the sample have to be in order for you to be able to tell the difference between the two? So that's, again, another computational model in which local things are relevant. And then, again, as a background for why I believe, so one of the things that made me believe that this is really a good approach to this important question of studying big graphs comes from this theory of graph limits. I don't know how well the audience knows this, but let me quickly go over this. This is a theory that with quite a few participants, I think the two main leaders of this are Nati and Balazs Szegedy, but there are lots of other excellent people who are involved. But just if you're interested, there is a wonderful book, recent book, that Lovas wrote about the subject. So if you're interested, and I highly recommend it, you can look at it. It's written beautifully, as he always does. The idea is this. So let me try and illustrate it from this perspective. So how can you, I mean, is it really feasible to learn something interesting from looking at these constant size profiles? So you would like, so let me state a theorem here. This is a major theorem in this whole theory. You have a series of graphs, and you would like, you seek a notion that the limit as n tends to infinity exists. And let me even call it W, which is the common thing. This is what's called the graphon in this theory. Under which conditions are we able to say that such a thing exists? So there are at least one very well studied and tested method that mathematicians have been using to define limits, which is whenever you have a distance anywhere, if you're in a metric space, then you can speak about a Cauchy sequence. This is small if m and n are large. So once we have a metric on graph, we can speak about Cauchy sequences, and therefore some notions of convergence to a limit, and you use something which is called the box metric, which essentially says, at least for graphs with the same number of vertices, what is the distance between two graphs? You try to match the vertices in the best possible way so that they agree on as many pairs as possible. And then there are some variations on this. And so the main theorem, a major theorem in this area, says that Gn tends to a limit in this sense, in the metrical sense, if and only if it has the following property. For every graph H, essentially if the profiles tend to a limit. So for every graph H, the density of H in Gn tends to a limit. So in other words, this concept of really coming from some infinite object or being generated by some, in this particular case, fairly simple method, these graphons, is equivalent exactly to agreement in the local profile. Please.
This is a single sequence of graphs as n-arranged?
Yes. And that's a necessary and sufficient condition. This thing exactly captures. So that's another reason why I really believe that this is okay.
What is the box metric?
The box metric, so it's easiest to explain if the two graphs have the same number of vertices. So what is the distance? You just take a one-to-one mapping between the vertices so as to minimize the number of pairs on which they disagree. So the least fraction of pairs on which you have to fix it, this is their distance. If they're, yes, you're with me? Sure. Okay, and if the numbers do not match, then think of a graph as being, we think of it as a matrix, the adjacency matrix. Think of it instead as a function of zeros and ones, and then what replaces this one-to-one matching is any measure-preserving map that you can do here on the same thing. Okay, so that's basic. Okay, so I hope by now you're convinced that this is a worthwhile undertaking to understand this. But are we completely in the desert with not at all. There is a lot of highly relevant and beautiful mathematics that we can use here. And this whole thing is closely related, of course, to perhaps the best developed part of combinatorics, which is extremal graph theory. So what do you do in extremal graph theory? Let me just quickly, I think, remind you stuff that you all know. So the grandfather of extremal graph theory is Turan's theorem, which you try to capture the intuition that if a graph has high density, has lots of edges, then you expect to find in it, let's say, big cliques and so on. And it tells you things like a graph of density bigger than r minus 2 over r minus 1 contains a kr. So in particular, plug here r equals 3. So you see that if a graph has density more than 1/2 and the bound is tight, so plug here r equals 3, you see that if a graph has density bigger than 1/2, it must contain a triangle. And this is tight because you can take this complete bipartite graph, and in general, you can partition your vertices into 3 parts for r equals 4, and so on and so forth. So this is a first case. So this is really the beginning of a really wonderful and deep theory. This is from the 40s, so it has been developed a great deal since then. And one of the main questions that people study in this area is this function ex of n and h. So this is the largest. So you can either think about it in terms of counting edges or density. It's the same thing. The largest number of edges in an n-vertex graph that contains no copy of H. So let me just say that as opposed to some stuff that we will do later on, this doesn't have to be induced. Okay, in a click it doesn't matter, but I'm not talking about induced. And so I'm Talmud says that if you give proper credit, you save the world. Okay, so I'm not taking this job on me today. So I'm going to be quite bad in giving credit. So my apologies to alive and dead people and those in between. Sorry.
Quantum superposition of life.
Yeah, exactly. Okay, good. The same theory with a little bit more of work tells you that this is n choose 2, so I chose to work with numbers, where chi is the chromatic number of the graph H. So if this number is at least 3, we plus little o of 1. So if H is a graph of chromatic number 3 and above, then we really have a very satisfactory answer here. And of course, one of the major problems in extremal graph theory is to understand what happens for bipartite. There we know much less, but just as a, for example, something that will show up later. So this is C4 is this graph, which is bipartite. That we know is theta of n to the 3/2, both upper and lower bound. So that is understood. But there are very few bipartite graphs for which this is known. So why is extremal graph theory so closely related to what we do? Because, of course, if you know the profile encodes, in particular, easily, it encodes the density of the graph, right? You can easily work out how many edges. If I tell you the K profile, you know how many edges the graph has. So this question about understanding the profile is much more general than one of these basic questions in extremal graph theory. Okay, so let me now mention, so I want to, okay, one major thing that I want to speak about, I hope I will have enough time to do justice to this, so at least let me for sure mention the name. So a major tool that has come into the arena a few years ago is Razborov's leg algebra method, which I hope to be able to at least briefly explain to you, because this, my feeling is that computer science are not sufficiently familiar with, so perhaps it's a good idea to speak a bit. Well, at least I see one expert in the audience, but still I think there are also non-experts. So perhaps I'll say a word about this. And the way I want to get to this is from the question that Razborov wanted to attack and solved, which is also still in the field of extremal graph theory. So in fact, I said that this is the grandfather of extremal graph theory. Honestly, there is actually even one generation earlier. This is from the 40s, but there is the case R equals 3 was done by Mantel, I think, in 1907 in quite a forgotten Dutch mathematical journal. So the case R equals 3. So if a graph has density more than a half, then it contains the triangles, and this is tight. But you could ask, okay, but let's say that it has density 0.6 or 0.73. Can we show that it must contain a lot of triangles? So the question was, so I want to take this and ask two very natural variations of this. So question one that I want to ask here is, given the density of G, how small can, you know what, let me already give this name. This is the density of triangles. Right now it's, well, perhaps not so strange that I call it P3, but this name will have more meaning or sense in a few minutes. So that's the chance that I take a triple and I find a triple of vertices and I find a complete graph. How small can this be? So when the density is below a half, the answer is 0. And from these pictures, you can guess, I think, it's not hard to guess what the answer is. And the answer is that essentially what you do is you move from this, when you're above a half, you do something like this, where these two are equal and bigger than this. So this is a unique construction, and that's the one that minimizes the density of triangles. And this, in fact, Rasborov proved using his method, which, as I said, I hope to at least give you an idea of. I'm starting to suspect that perhaps not. So this is one question that is now completely solved. Another question on which Rasborov made great progress, but is still not solved, and was asked already by Turan. So Turan's problem for 3 uniform hypergraphs so now we are not dealing with graphs, but with collections of triples. And you ask the most natural first question. In fact, you come back to Mantel, and you ask something like, which number of triples forces. So in the same way that a triangle is the first non-trivial dense thing, so it forces this thing, 4 points and all the triples on them. And again, there is a natural, here things start to get more complicated because the thing that is conjectured to be the optimal is not unique. And as any one of you who ever solved an extremal problem knows, many extrema make such questions usually difficult. And this has been open for 70 years, certainly one of the most highly considered or highly regarded questions in combinatorics. And Rasborov was able to make very nice progress on this, so he holds the world's record at the moment and various other things, but the question is still open. So all these things really, I hope, give you some idea on the fact that when we want to deal with this question, we are completely, it's really not that we are on our own. There is theory to draw on. So let me mention 2 more concepts that are related to this idea of local profiles, which are very important, but again, I won't be able to do them justice. This is always confusing. This is quasi-randomness. So speak and not pseudo. Quasi-random graphs. So, of course, the most, again, I'm assuming that you all know, the most basic construction of random graph is G and P, where every pair of vertices are adjacent independently and with probability P, and quasi-random P is saying that this is similar to G and P. And here I just want to, so again, you're looking at the profile, and one of there is a beautiful, again, at least I should mention a name. So Andrew Thomason started this, and there is this famous and beautiful theorem of Chang, Graham, and Wilson. So what does this mean? Their basic theorem says that there is a list of 7 or 8 properties of graphs which capture the fact that graph locally looks like this. So the density is very close to P. There is a whole, but the most amazing part is that this is equivalent to the fact that the number of, and now let me be, of induced C4s is correct. So I'm being very shallow here, but it would take me a little bit more time to say this. So I just want to give you the highlight of this. So if you want to understand the local, so this in particular, if this is correct as it should be in GNP, so then it follows that the whole K profile is as in GNP. So it's not a difficult theorem at all, but it's a very surprising fact if you see this for the first time. So this is one type of property or behavior of local profiles that we may consider. Another thing which is more subtle, but as you'll see, very fascinating and again, very mysterious, and I think again quite relevant possibly to practical situation, is K universality. So that's a definition now. I'm not telling you a theorem, but a definition. You say that G is K universal if it has a full K profile. So every K vertex graph appears there with positive probability. As I expected, I am in trouble with the time. So, okay. Let me. So I think I hope I gave you enough of an overview on this thing. Now let me try and get a little bit into some details or get more concrete about specific questions. Let's just speak about the 3 profile. The 3 profile. So what is there? Well, what kind of 3 vertex graphs are there? There is this. The probability of this I call P0, P1, P2, P3. So here is a very concrete question. What such 4 tuples are possible? Now let me just make sure I'm not interested in all sorts of strange phenomena that happen in small graphs. I only want to understand what happens for large graphs. So I'm looking at this subset of R4, which consists of all x0, x3, such that there exists a sequence of graphs that go to infinity with P super 3 of G tending to this vector X. What is this set? It's a 4-dimensional set. In fact, it's 3-dimensional because, of course, these numbers add up to 1. And we'd like to understand this. So this theorem this theorem of Rasborov gives you information. Here is one more piece of information that this is stuff that we know from the 60s, which is a cute, nice exercise, which I will not do because I'm starting to be short on time. But that's an easy and nice thing. So, for example, even answer the question, what are the possible values of P0, P3? So in recent work with, well, at least my co-authors, I have to mention by name, Wang, Navis, Peled, and Sudakov, we are able to derive information about this. And for example, we are able to tell what are the possibilities for P0, P3. In particular, this set is not, if you wondered, this set is not convex. It has all sorts, it's a strange set. We know various things about it. And we understand also with the same people what is possible when it's triangle free. We have a full description of that. Using this method of flag algebras, we're able to solve this case. But just to illustrate how bad the situation is, let me tell you one very fascinating fact, which I find really important and completely not understood.
Nati, is there a set of limit objects for such sequences that you can study instead of studying?
I don't know. If you have such an idea, I would really be glad to. It's a good idea, but I don't know. No.
Actually, see if I understand the question. There's the more restricted question of whether you can produce a particular graph limit that achieves each point. That achieves
What is achievable? Just what is achievable? I don't even. So a four tuple here is in the set. If you can find let me say it, for every epsilon and every n, you can find a graph bigger with more than n vertices whose free profile is epsilon close to this point.
I understand the definition, but maybe what James was asking is, okay, there's a more restricted set of points which you can actually achieve as a particular graph limit, where the whole sequence of G.
No, it's the same thing. That's the same thing. That's the same thing, right?
But your limit, whatever objects, your graph funds might contain
Right.
more things than you can achieve with graphs.
Right,
That's-
right. He speaks about things using things which are not necessarily graphs. Okay, but okay. So I think these are okay. There are things here which it seems to me this theory of graph limits is unable to capture, and I hope there is. Friedgut likes to make fun of me because I once told him that I wanted, when I was a child, I was hoping to discover some lost continents. So this is the closest that I get to this. So let me tell you what it is. So let's look at this. Let's look at this inequality. This inequality is tight. Why? Because in Gn1/2, obviously both P0 and P3 are an eighth. So this made Erdős ask the question or conjecture. Well, I give it these strange names. So now we move on to, let me put it this way. With 3 vertices, it's conceivable that we're able to answer this. But with 4, we're really in bad trouble. We really don't understand the situation. So let me illustrate with this. He asked whether this is bigger than 1 in 32. So this is for 4 vertices, the empty graph and the complete graph. Why? Again, each one of them, 1 in 64, and you get 1 in 32. And this is not true. Thomason refuted it. Now, his graph, and then Redl and students, these graphs are very strange. They we don't understand. We don't know. We have no good guess on where the minimum of this is. And this is, for me, an indication, for example, that when we're dealing with Ramsey's theorem, the best lower bounds that we know today come from Gn1/2 or GNP for when they're. And this indicates to me, I think what this is trying to tell us is that this is not the right place to look. This is an indication of a lost continent. We really have such a small variety of graphs that we know and work with. And this is, and there are lots of other things which I already see I won't be able to get to today. These are indications that there exist graphs of types that we really don't know. So I think this is much more than an incidental thing. I think this is an indication of the existence of very interesting graphs that we completely do not know. So what I want, since I see I'm really short on time, is at least spend a few minutes on local to global. Because here there is one of the most beautiful and profound open questions in combinatorics, which at least I want you to be aware of. In fact, I'm erasing exactly what's relevant here, this notion of universality. So this is the Erdős-Heinel conjecture. Amazing conjecture. And it says the following. For every h, there exists an epsilon positive such that if G is an n-vertex graph with no induced copy of H, then at least one of the two, either alpha of G or omega of G, is at least n to the epsilon. Okay, this is the clique number and independence number of the graph. Now, let's understand what this says, and I hope I can convey to you my excitement with this question. In general, in an n-vertex graph, a random n-vertex graph has a clique and an anti-clique of log n. That's it. That's the largest, and it's really beautiful. If never saw this, but really one of the fundamental discoveries of the probabilistic method. Great. What this says that if your local profile for some fixed k is incomplete, if you're not k universal, this has a huge impact on the overall structure. So the clique and anti-clique, one of them at least, must jump from logarithmic to a power. Let me tell you, so just a poor man's, I don't know, version of this, something recent that I did with the students. So this is really, the result here is really simple. It's the technical, not particularly difficult, but I think it suggests something that may be very interesting. And so this is a recent result with a student of mine, Avram Morgenstern. It says the following. If P0 and P3 are less than this number, then G is free universal. The important thing about, and the result is tight. So the important thing is that this number is above 8, an eighth. So if I wrote here 1.24, then I could say that this graph is made of gold, because such graphs simply do not exist. So that would be true, in an empty way. But there is a bigger number. So what this suggests to me is that this is a tip of an iceberg. That perhaps that's another, that perhaps there exist theorems of this general type, so that you don't have to forbid a particular graph, but it's enough if you limit how often you see them. If you put upper bounds on those, then.
So you have a conjecture that extends it?
No, I can no. So no.
Make a conjecture of this.
You know me. I love if I could, I would have done it ages ago. I wouldn't wait for you, Gil. So I can tell you in particular, in this case, we know that this doesn't imply 5 universality. About 4, we don't know. But as I say, this result per se is, the proof is a proof, numbers, some optimization, you prove it. So I think in itself, this is not particularly, super duper, but it's
You probably need to look at larger.
presumably. But I don't have, at the moment I don't even have a good conjecture. My meta conjecture is that there could be theorems of this general flavor, but I don't have anything concrete to work with. So I think it seems like my time is up. There is still a lot of things that I could have told you, so if you catch me in the corridor, I'll be happy to share them with you, but it's time to stop, so I stop.
More questions?
Just quickly, what's 3 universal mean?
That you get all three possibilities, all these 4 possibilities are there. P1 and P2 are positive as well.
About these profile sets, is there any general information about those, like they're semi-algebraic sets and some general principles?
I wonder. No, I don't think anything like this is known. No, that would be interesting to tell. I'm not even sure that this is, even very basic things like this are unknown. But perhaps, you see, so, I've already mentioned there can't be a talk in combinatorics without some mentions of Erdős. So let me tell you one more of his favorite stories. He used to say, R33, the Ramsey number is 6. That probably you saw in high school. And R44 is 18. And we don't know R55 and R66. So he used to say that if the Martians land on planet Earth and say, either you tell us what R55 is or we blow this planet, then you should get all the mathematicians, all the computer scientists and all the computers and try to... But if they say the same thing with R66, then the only plausible thing is to try to fight them back. And I feel something a bit similar about the 3 profiles of graphs. I believe that this is something that with enough effort, this is... there are still many things that we don't know, but this is within reason. It seems to me, at least if nothing else, because of this counterexample of Thomason that I said, that the passage from 3 to 4 there is we really are in open waters. The situation there is very poorly understood. Doesn't mean that we have to, we can ask questions like this. We can get bounds, if not tight, at least we can do something. But the whole thing is still very mysterious. Let me add one more thing, one comment, which I didn't even get to mention. I spoke only about graphs, but you can also speak about the local theory of permutations, which is very interesting. There are some nice things. There are tournaments. Almost every combinatorial object that you think about, you can speak about local phenomena and local to global phenomena. It's really a very rich subject.
What do we know exactly about this conjecture? Is there something that was proved? Maybe a
Yeah. So Erdős and Heinel themselves proved this, which is already, it's not difficult and very, very pretty, very clever, but it's a clever but not a very difficult proof. So that already is the first open case is this. It's not known if H is C5.
For all graphs of 4 vertices of U,
right, yeah. But what happens is, the excellent people have done really very impressive work on this, but so far all the H's for if you know what that is, all the H's for which this is known are perfect. So the first imperfect graph is C5, and this is the first case that we don't know.
Nati,
Please.
did you say what 0.1591?
It's a construction. It's a specific construction, and we are able to show that this construction is the... You can find it on my homepage. So, I certainly don't want to say anything bad. It's a student's work, but... And it's a decent work. We're going to publish it. I'm happy with it. Everything is good. But I think the main point in this paper is not so much this particular result, but just the possibility that this really reveals, hopefully, a new type of, a very general phenomenon.
But the answer can't be really 0.1, is it?
No, it's a number. It's something. There is some fourth degree equation, and then you take the root and you do this with that, and stuff like this. No, it's some.
I was surprised that was tight.
Yeah.
Could you say something about the Thomason's graph construction?
Okay, so I can say something. No.
I was going to ask you the same thing, but people should be. And I will keep you going for another 20 minutes.
As you want.
People should feel free to leave if they're not interested in that.
Yeah. So so I can tell you one thing about this. I had at least 2 graduate students who I tortured with this problem, and both of them asked me to switch subjects. And they both did, and they both did very well. So this is just, okay, I'll say more about this, because in hindsight, there was also something a mistake that I made. Okay. What I'm unhappy about, it's really funny, because I'm very friendly with Andrew Thomason, and we meet often in Oberwolfach and so on, and over, I wine, he beer, discussed this at length, and at some point he said, I didn't even know that this was such a great result. You convinced me it's a great result, so I think it's a great result. But both his and the Redl result are bad in the sense that they construct a finite graph and they blow it up. The Franeker-Redl is something that I wouldn't do this now, but if you want, I can show this to you in private. You start from a graph with 2 to the 10 vertices. There is a very simple rule on how this graph looks like, and then you blow it up. So far, this is this project that I had 2 students give up on to find an honestly asymptotic counterexample to the. I don't view this as an honestly asymptotic. I mean, it's perfectly okay and extremely interesting, but I still think that we are looking for an honestly asymptotic counterexample to this Erdős conjecture, and that we still don't know. I can also tell that in hindsight, some of the things that we tried, and I should have seen this, but I didn't, was that some of the things that we tried, it was really a stupid mistake on my side, because they were quasi-random, and quasi-random cannot refute this. So you have to be, one thing, if you're thinking about this problem, beware of quasi-random examples. They're not going to solve your problem. So that's one simple warning that I could add.
And how big is the Thomason basic graph?
It's not huge. There are, I don't know, 100 or things like this. He has more.
Wrote down 100.
No. There is nothing that, no, they're very clever. And he wrote about these 3 papers. Each time he gets this thing to be more conceptual and so on. But really, if you want the simplest to describe example, then it's the Franeker-Redl. So let me say 2 more words. You take all the binary vectors. Here is what it is. You take all the binary, you partition the number from 0 to 10 into 2 parts, and part A and part B. You take all the 2 to the 10 vertices, and you connect two guys with an edge if their Hamming distance is in part A. That's it. So all you have to, the whole thing boils down to partitioning the set 0 to 10 into 2 parts.
Is it possible to explain in like 2 words why S is not convex?
Yes. Here is this is something I intended to do, but you see, you can have, of course, P0 is 1 and P3 is, and everything else is 0, and you can have P3 is 1, just the complete graph and the empty graph. But, so that's one of the things that we did with Sudakov and his student, and with my student Yuval Peled, something like this. There are 2. That's the possible range of the pair P0, P3. So that's the P0 axis, P3 axis. You see that it's not convex. In particular, this started from a question that I had initially thought was going to be just a little exercise. I want to show that, so when you see this and when you think convex, you ask yourself, is it possible that both of them are a half? If you think about it for 2 minutes, you realize this is impossible. And I wanted to find out a best theorem of this sort that says at least one of them is at most something. And indeed, this is one of the things that, and which I thought was going to be an exercise, but no, it was fairly hard. I don't have, I will not tell you now, but in some sense, again, this is not discovering any new continent, but it's difficult. That I can say, this is difficult, and I think any combinatorialist would tell you, and even some computer scientists, if you think about it, I think if you have any exposure to experimental graph theory, you would think very easily that the best construction for such a thing is, well, if you use it, we used to say a red island in a blue sea. So you take a subset of the vertices, you connect everything by red, you see everything here is red, and all the rest of the edges are blue. And now you have to optimize on which fraction of the vertices are here. You write, so the theorem is that always the smaller of these is 0.26 something, which is again a number that comes from optimizing all this. But no, it's far from being even the Razborov area. No, it's not convex. It's far from convex.
This is the optimal.
That's the optimal. This is. So when you do this, what's blue and what's red, you get these 2 curves. That's the upper, and then we prove a theorem that says that everything in between can be realized. And
what are the edges between the 2?
No, they're blue. So everything here is red, or everything here is edges, and everything here are non-edges, or the opposite.
Any more? Okay, we'll continue at 3. Thank you.